The Milky Way is a magnificent cosmic structure, home to billions of stars and trillions of planets. Surrounding them are vast clouds of interstellar dust and streams of superheated gas. Together, they create the intricate and beautiful tapestry we call a galaxy. Tonight, we invite you to take a remarkable journey through it. Our path begins at Alpha Centauri, the closest star system to our Sun. Moving hundreds of times faster than light, we'll visit the most remarkable nearby stars, then pause at an extraordinary planet entirely covered by an eternally boiling ocean. We'll venture close to a restless, pulsating giant living out its final millennia, then visit some of the most extreme and challenging exoplanets for survival. Following this, we'll approach the most mysterious and dangerous objects in the Milky Way, black holes, before taking a swift flight through the galaxy, traveling from its brilliant center, pierced by stellar radiance, to its distant edges, where mysterious dark matter hides. Prepare yourself. We're beginning our journey, Alpha Centauri, our nearest stellar neighbor. For nearly a century, Earth has been sending vast amounts of structured radio signals into space. Earth's radio noise has already reached dozens of other star systems, including Arcturus, located 37 light-years away, and Aldebaran, approximately 65 light-years distant. These signals might also be heard on the surfaces of numerous potentially habitable exoplanets, such as Ross 128b or Gliese 667 cc. However, the Alpha Centauri triple system remains the Sun's closest stellar neighbor, making it the most obvious candidate for humanity's first interstellar voyage. Alpha Centauri is a multiple star system consisting of 3 components. The 2 largest are located relatively close to each other and appear as a single point of light to the naked eye. They orbit a common center of mass in slightly elongated elliptical paths, completing one full revolution approximately every 80 years. The maximum distance between these stars can reach 35 astronomical units, while the minimum distance is about 11.2 astronomical units. The distance between our Sun and these objects is approximately 4.36 light-years. The most massive, largest, and brightest component is called Alpha Centauri A. It's a main sequence star whose mass exceeds the Sun's by about 8%, with a radius approximately 1.22 times that of our star. Despite Alpha Centauri A having a surface temperature and spectral class similar to our Sun, it emits 1.5 times more light energy. Currently, no confirmed exoplanets have been found in this star's vicinity. However, in 2021, infrared observations revealed evidence of a potential planet-like object. Preliminary calculations suggest its mass ranges from 9 to 35 Earth masses, with a size between 3.3 and 7 Earth radii. This hypothetical body orbits at a distance of 1.1 astronomical units from its parent star, completing one revolution in approximately 1 year. This data requires verification through additional observations, which could be performed by the James Webb Space Telescope or ground-based observatories. The second component is called Alpha Centauri b, or Ptolemy, and it's also a main sequence object. However, Its mass is about 10% less than the Sun's, and its radius is approximately 0.86 times our star's. Additionally, this star is slightly cooler than the Sunday. Its surface temperature is about 5,260 Kelvin, or just under 9,000 degrees Fahrenheit. This combination of factors gives the star an orange color, and its brightness is on average half that of our Sunday. Compared to other stars in its class, Alpha Centauri b emits much more energy in the X-ray spectrum. The star has a restless character, with its surface periodically producing bright flares and eruptions. No confirmed exoplanets have been found near this star either. In 2012, based on analysis of the star's proper motion over 4 years, astronomers from the Geneva Observatory suggested the existence of a very close planet with an orbital period of about 12 days and a radius slightly smaller than Earth's. However, 3 years later, during additional verification, a mathematical error was discovered in the data processing, and the planet's existence was disproven. The third component differs significantly from its companions. It's a red dwarf with a mass about 12% of the Sun's and a size roughly 7 times smaller. Its surface temperature barely exceeds 5,400 degrees Fahrenheit, and its luminosity is a mere 0.17% of our Sun's. Of all Alpha Centauri's components, this dim cosmic object, located 4.25 light-years away, is the closest star to our Sunday. Thanks to this fact, it received the name Proxima Centauri, meaning nearest in Latin. Moreover, the distance to this object is gradually decreasing, and in 26,700 years, it will be just over 3 light-years away. Nevertheless, due to its extremely low brightness, this star isn't visible from Earth with the naked eye. Proxima is noticeably distant from the other 2 components of its stellar system. Currently, this distance is about 13,000 astronomical units, or 0.21 light-years. However, over the next 300,000 years, it will gradually decrease to 4,100 astronomical units. The star completes a full orbit around the common center of mass in 547,000 years. Unlike its larger neighbors, Proxima's planetary system was discovered more recently. The first planet, named Proxima Centauri b, was detected in 2016 using the radial velocity method. 4 years later, in 2020, its existence was confirmed through spectroscopic studies using the VLT, the world's largest ground-based telescope. According to refined data, the exoplanet is located approximately 0.05 astronomical units from its parent star and completes one full orbit in about 11 Earth days. Calculations show its mass exceeds Earth's by 10 to 20%, and its radius is about 1.3 times Earth's. According to mathematical modeling results, Proxima Centauri b receives approximately 1.5 times less thermal energy from its star than Earth does from the Sunday. Its average temperature is 234 Kelvin, or minus 39 degrees Fahrenheit, meaning liquid water could hypothetically exist in some regions of the planet. However, due to its extreme proximity to the star, the planet is likely tidally locked, constantly facing the star with one side, A dense atmosphere could smooth out the inevitable temperature differences in such conditions. But Proxima Centauri, like many red dwarfs, frequently displays powerful stellar material ejections and ionizing radiation flares. It's assumed that such stellar activity gradually destroys the atmospheres of nearby objects. A powerful magnetic field surrounding the planet could protect against this destructive process, but the probability that Proxima Centauri b possesses one is extremely low. In 2020, the existence of a second planet in this system was proven. The cosmic object, named Proxima Centauri c, is separated from the system's center by about 1.5 astronomical units, and its orbital cycle is just over 5 years. The object's mass ranges from 6 to 8 Earth masses, and its radius hasn't been determined yet. Depending on its size, this exoplanet could be classified as either a mini-Neptune or a super-Earth. Due to its great distance from the parent star, Proxima Centauri c's temperature is extremely low, approximately 39 Kelvin or minus 389 degrees Fahrenheit. Also, according to some observations, the planet may have a ring system about 5 Jupiter radii in size. Additionally, analysis of recent VLT telescope data suggests the presence of a very small exoplanet with a mass of about 0.25 Earth masses, located approximately 0.0029 astronomical units from the parent star. If it truly exists and isn't a measurement error, then a year on this planet would last about 5 Earth days, and the surface temperature would reach 360 Kelvin or 187 degrees Fahrenheit. However, the reality of this cosmic object remains highly questionable and requires additional confirmation. Alpha Centauri has been listening to our radio signals for over 100 years. However, crossing the 25 trillion miles of cosmic void that separates us remains impossible. Light requires more than 4 years for this journey, but humans can currently only dream of such speeds. Even the fastest modern spacecraft would spend tens of thousands of years in transit, though using progressive technologies could theoretically significantly reduce this time frame. Since the very dawn of space exploration, many projects for ships hypothetically capable of crossing interstellar distances have been created. However, none have been realized in practice. Most of these missions have been forgotten, but one is still active. We're talking about a program called Breakthrough Starshot, which plans to send an entire 1,000 microprobes to Proxima Centauri in the first half of this century. Their size will be no more than a centimeter, and delivery is planned using a thin, strong sail accelerated by pulses from a super powerful ground-based laser. According to calculations, the interstellar probe will leave the solar system at a speed of about 20% of light speed, and the total travel time will be approximately 20 years. Another nearly 5 years will be required for the data collected by the mission to reach Earth. Barnard's star, the fast mover, moving 6 light-years from the Sun, will reach our first target, the small red dwarf GJ 699, also known as Barnard's star. It's notable for moving across the sky at an incredible speed, capable of crossing the Moon's disk in just 180 years. The reason lies not only in the small distance to the object, but also in the star's very fast proper motion. Barnard's star is approaching the solar system at a speed of just over 60 miles per second and will become our nearest star in approximately 10,000 years. By that time, the distance between it and the Sun will be only 3.8 light-years. However, even at such a distance, the red dwarf's dim glow won't be enough to see it without optical instruments. The star's mass is only 17% of the Sun's, and its radius is approximately 6 times smaller. Like all red dwarfs, Barnard's star is quite cool. Its surface temperature is only 5,182 degrees Fahrenheit. Given these parameters, it's unsurprising that the object's luminosity is 2,300 times lower than our Sun's. In 2018, results from 20 years of observing the star's proper motion were published, potentially proving the presence of a nearby exoplanet. Available calculations show it's a cold super-Earth with a mass of at least 3.2 Earth masses. The planet, named GJ 699b, is located about 0.4 astronomical units from the system's center and completes one full orbit around its parent star in 233 days. Unfortunately, the exoplanet's orbit is positioned such that it doesn't pass between Earth and its parent star, making spectral analysis of the object nearly impossible. Nevertheless, mathematical modeling can provide us with some information about it. Since Barnard's star is very dim, its planetary companion receives 50 times less energy than Earth does from the Sunday. For this reason, the temperature on the celestial body's surface is extremely low, only 105 Kelvin or minus 272 degrees Fahrenheit. However, we can't exclude the possibility that tidal disturbances or radioactive decay in the planet's interior released enough energy to form a warm subsurface ocean. If this is indeed the case, potential life in its depths would have had enough time for unhurried development, as Barnard's star is apparently among the most ancient known stars. According to calculations, its age exceeds 10 billion years, which represents only a few % of the star's expected lifespan. Thanks to its proximity and favorable direction of movement, Barnard's star is one of the priority targets for potential interstellar travel. Whether artificial spacecraft will one day reach it, only time will tell. Sirius, the brightest star. Meanwhile, on the other side of the Sun lies almost the complete opposite of a dim red dwarf. We're talking about Sirius, the brightest star in the night sky, located 8.6 light-years from our planet. To Earth, this star appears as a single light source. However, closer investigation revealed it's not a single object, but a binary star. Currently, both system components are at maximum distance from each other, about 30 astronomical units apart. The primary star, also called Sirius A, is a bright blue-white star with twice the Sun's mass. Its diameter exceeds the Sun's by 70%, and its surface temperature reaches 18,000 degrees Fahrenheit. Thanks to this, Sirius A radiates 25 times more energy than our star. The second object, known as Sirius B, is barely noticeable against its bright and massive companion. It's a white dwarf with a radius of about 3,000 700 miles, and a mass very close to the Sun's. Like all stars of this type, its surface temperature is extremely high, reaching 45,000 degrees Fahrenheit. However, due to its small size, this white dwarf is approximately 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in Sirius's vicinity. The reason may lie both in the star system's young age and in the special position of its ecliptic plane. Because of this, hypothetical exoplanets don't pass between the light source and Earth, meaning they can't be detected by the transit method. Another hypothesis states that approximately 120 million years ago, Sirius B exhausted its stellar fuel supplies and transformed into a red giant. Soon after, it shed its outer layers, becoming a compact and very hot white dwarf. As a result, the protoplanetary gas dust disk that then surrounded the young star system was destroyed by this explosion. Its remnants dispersed into surrounding space, depriving forming planets of any chance of survival. Currently, both system components move around a single center of mass in moderately elongated orbits, completing a full revolution every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more noticeable in the night sky. The minimum distance to it will be about 7.5 light-years, after which the system will begin slowly moving away from us. This situation will continue for another approximately 660 million years, after which Sirius A awaits the same fate as its companion. For a brief time, a powerful flash will increase its luminosity thousands of times. However, within several months, the star will completely fade, disappearing from the sky forever. Wolf 1061, a system of 3 worlds. Leaving Sirius's vicinity, pierced by deadly ultraviolet radiation and stellar wind, will maneuver near the solar system to reach a small star located 14 light-years from Earth. In various catalogues, it's known by different names, one of which is Wolf 1061. This star is a red dwarf with a radius about 30% of the Sun's. Its mass is approximately 4 times less than our star's, and its surface temperature equals 5,930 degrees Fahrenheit. Like all objects of its class, Wolf 1061 is extremely dim. Its luminosity is only 0.14% of the Sun's, so the star isn't visible from Earth with the naked eye. However, this red dwarf possesses one of the most numerous and diverse planetary environments among star systems closest to us. 3 exoplanets have been discovered in its vicinity, and all are rocky and similar in composition to Earth. The conditions on each of these 3 bodies differ substantially. The first and closest exoplanet to the parent star is called Wolf 1061b. It's located 0.038 astronomical units from the system's center and completes 1 full orbit in approximately 5 days. The object's mass ranges from 1.5 to 2 Earth masses, and its radius exceeds our planet's corresponding parameter by 20%. It's quite probable the celestial body is tidally locked and constantly faces the star with one side. For this reason, the temperature on the object's day side is extremely high, and flares and stellar wind from the nearby star practically exclude the presence of an atmosphere. All these factors make the exoplanet absolutely unsuitable for the emergence and maintenance of life. The system's second object, Wolf 1061c, is located 0.089 astronomical units from the star and completes one full orbit around it in approximately 18 days. Thus, it lies within the star's habitable zone and can be considered a potentially habitable celestial body. Wolf 1061c is approximately 3 to 4 times more massive than our planet and belongs to the super-Earth class. Observations show its radius is about 1.6 times Earth's, and surface gravity, according to calculations, is 60% higher than our familiar value. The exoplanet receives noticeably less energy from its star than Earth does from the Sun, so its equilibrium temperature is substantially lower. It's 223 Kelvin, or approximately -58 degrees Fahrenheit, which is slightly higher than Mars. Nevertheless, considering daily and seasonal temperature fluctuations, liquid water could exist on the celestial body's surface. With a dense atmosphere exhibiting a pronounced greenhouse effect, this probability is even higher, and conditions on the planet could approach comfortable levels. Of all potentially habitable exoplanets known at present, Wolf 1061c is among the closest, occupying 5th place on the list. The system's third object is known as Wolf 1061d. It moves in a noticeably elongated orbit, at whose farthest point the distance between planet and parent star reaches 0.73 astronomical units. The orbit's perihelion is located much closer to the system's center, only 0.21 astronomical units away. A full yearly revolution for the celestial body takes approximately 217 Earth days. According to calculations, Wolf 1061d's mass is about 7.7 Earth masses. If this celestial body is a rocky object, its radius equals approximately 1.7 times Earth's. If the planet is a mini Neptune with a thick, multi-layered atmosphere, its size should be no less than 2 times our planet's diameter. Despite the orbit's comparatively high eccentricity, Wolf 1061d never enters its star's habitable zone. Apparently, the celestial body is unsuitable for supporting life, but may present great scientific interest from the standpoint of planetary evolution. This system is one of the priority targets for future research, so it's quite probable that new discoveries will soon be made there. Among other things, Wolf 1061 is notable for being located almost at the very edge of the so-called local interstellar cloud. It represents a region of space filled with hot but extremely rarefied hydrogen. Its temperature is about 12,140 degrees Fahrenheit, and in 1 cubic centimeter of space, you can find on average only 0.3 atoms. This is approximately twice less than the Milky Way average. The solar system has been moving through the local cloud for the last 10,000 years. Its average diameter is about 30 light-years, but our system is located almost at its very edge. For example, Alpha Centauri is already in the neighboring G cloud. We'll spend another about 2,000 years within our own cloud, after which we'll enter an even more rarefied and hot region. AP Columbi, the runaway star. Continuing our path through cosmic space, we'll soon discover a rather unusual star named AP Columbi, located 27.4 light-years from Earth. First, it attracts attention because it was born just 40 million years ago, in those times when dinosaurs had long been extinct on our planet. Even more amazing is that this event occurred in a completely different area of the galaxy, 450 light-years from the object's current position. Usually, young stars remain near their stellar nursery for a sufficiently long period, up to several hundred million years. If we analyze AP Columbi's proper motion, it turns out it apparently once belonged to the open cluster IC 2391. It numbers about 30 stars, united by common origin and direction of movement. However, several million years ago, one of them exploded, disrupting the established fragile equilibrium of numerous cosmic bodies. This catastrophe gave the young star an additional impulse, forcing it to swiftly leave its birthplace. Being a very small red dwarf with a mass of only 13% of the Sun's, this star emits 4 times more energy than any other known celestial body with similar parameters. Moreover, its radius is twice the value calculated according to modern stellar structure theory. Strangely enough, another unusual feature of the star helped provide answers to these mysteries. The fact is that according to spectral analysis of its radiation, AP Columbi's stellar material contains an anomalously large amount of lithium. Usually, this element is abundant in protostellar clumps, but quickly burns out after the thermonuclear reaction begins. This means this star is a very young forming star that hasn't even entered the main sequence phase yet. Consequently, AP Columbi is characterized by instability and an explosive character. It's subject to strong flares and stellar material ejections, during which its luminosity can briefly increase up to 10 times. Usually, such phenomena threaten nearby exoplanets, stripping their atmospheres and sterilizing their surfaces with ultraviolet radiation. However, observations show there are no large cosmic objects within 4.5 astronomical units of this star. Apparently, its age is too small for the formation of full-fledged planets. Nevertheless, it's a unique cosmic body, very important for understanding the process of early stellar evolution. Gliese 370. A warm ocean world. As we've been able to confirm, not every star has planetary systems. Therefore, our next stop is located near the orange dwarf Gliese 370, which is 37 light-years from Earth. In 2011, a single exoplanet was discovered near it, receiving the designation Gliese 370b. The object was discovered using the radial velocity method and has a mass of 3 to 4 Earth masses. According to modern concepts of celestial body formation, the discovered world is most likely a rocky planet whose radius is approximately 30% larger than Earth's. In such conditions, gravity on its surface should exceed our familiar value by at least 40%. Gliese 370b is located 0.26 astronomical units from its parent star and completes one full yearly orbit in 54.4 Earth days. Thus, the exoplanet is in its star's habitable zone. If its surface albedo value is close to Earth's indicator, the celestial body's average temperature should be approximately 77 degrees Fahrenheit, which is several degrees higher than on Earth. The fact that the exoplanet is located far enough from its parent star allows us to assume it's not tidally locked and has its own daily cycle. This promotes more even heat distribution across the celestial body's surface and, consequently, may cause a milder climate. Moderately high gravity should smooth the planet's relief, which combined with abundant liquid water may cause the formation of spacious seas, warm and shallow. Such places are traditionally considered most comfortable for the emergence and maintenance of life. At the time of discovery, Gliese 370b was considered one of the most attractive exoplanets for potential biological life. However, later studies allowed us to assume conditions on its surface are somewhat less comfortable than previously thought. In particular, there's a probability the celestial body's atmosphere is too dense and has a pronounced greenhouse effect. Nevertheless, even by the most pessimistic forecasts, the average surface temperature doesn't exceed 172 degrees Fahrenheit, corresponding to a temperature range from approximately 86 to 212 degrees. Considering that our planet's climate in the Archean period was approximately the same, Gliese 370b remains a very attractive exoplanet for searching for extraterrestrial life. This means its research will continue, the local bubble and beyond. If we stop for some time and look around, we'll discover we've moved away from the solar system by more than 50 light-years. Within this radius are located over 1,000 stars, most of which are single. Other objects are binary or even represent entire groups of stars. The brightest example of this is Castor, a complex, amazing system consisting of 6 components at once. This star system is located 50 light-years from Earth and is visible to the naked eye as a single light source. Being the second brightest object in the Gemini constellation and 23rd in the entire starry sky, Castor has been known to people since ancient times. Since the system numbers 6 full components, it has a rather complex structure. The 2 brightest of them, Castor A and B, are blue-white stars similar to Sirius, each having a nearby companion, a red dwarf. The distance between the centers of mass of these binary stars is about 110 astronomical units, and they require 445 years for a complete revolution. Approximately 600 astronomical units from Castor A and B is located another close binary system consisting of a pair of very similar red dwarfs. Each has a mass of about 0.6 solar masses and a surface temperature of approximately 6,560 degrees Fahrenheit. Both stars are located so close to each other they spend less than 20 hours on a complete revolution. They move around the common center of mass of the entire system in a very elongated elliptical orbit with a period of about 14,000 years. Until now, not a single confirmed exoplanet has been discovered in the Castor system. However, if they do exist, they're most likely located here, near the system's dimmest component. For example, in 2018, astronomers discovered fluctuations in Castor C's orbital period, from which it follows that near it may be a brown dwarf approximately 49 times more massive than Jupiter. According to calculations, it's located 14 astronomical units from the parent star and completes one full orbit around it in 54 years. It's not excluded that, like many red dwarfs, Castor C has rocky exoplanets located close to the star. In this case, the sky of such a hypothetical object should present a truly incredible spectacle. On one side, a substantial part is occupied by two crimson stars endlessly circling the sky, and on the other, eternal twilight is dispersed by the light of a pair of stars, each hundreds of times brighter than Earth's moon. Whether this is really the case is currently impossible to verify. Despite the fact that the stars we've visited are separated by enormous distances, they all belong to a single structure with a total extent of about 300 light-years. It's called the local bubble, and includes not only thousands of stars but also several large structures, including the local interstellar cloud. The local bubble formed as a result of sequential explosions of several supernovae that occurred between 10 and 15 million years ago. It represents a giant cloud of interstellar gas heated to 1 million Kelvin. Due to the high temperature, the gas tends to expand, so its density is approximately 10 times lower than the galactic average. In addition, hot ionized hydrogen constantly emits X-ray radiation. However, the Sun and Earth's magnetic fields, as well as the planet's atmosphere, successfully protect us from deadly radiation. The local bubble borders other similar formations. For example, slightly to the side of the solar system's direction of movement is located the so-called Lupi bubble, formed by supernova explosions in Antares's vicinity. For a long time, this giant cosmic structure has been actively interacting with our bubble, which has caused the formation of grandiose condensations located in the border area. The neighboring bubble's center is removed from us by approximately 500 light-years, and in several tens of millions of years, the solar system will reach its edges. Clouds of superheated gas and scattered clusters, giant nebulae and stellar streams. All these majestic cosmic structures fold into single systems called galaxies. In turn, they unite into galactic filaments, giant streams and walls, billions of light-years long. This is how the universe's large-scale structure forms, hiding countless numbers of the most diverse stars and worlds in its depths. Who knows what we'll find among them? Gliese 1214b, the ocean planet. The first steps toward theoretically substantiating the existence of planets completely covered with water were taken back in the 1970s. It was precisely at this time that it was proven radioactive decay in planets' interiors and tidal forces could lead to water ice melting and the formation of giant oceans. Similar processes most likely occur on Jupiter and Saturn's moons, but due to great distance from the Sun, these celestial bodies remain bound by thick ice crusts. However, when it comes to ocean planets, we usually mean a slightly different type of cosmic body. It's assumed the ocean on the planet isn't hidden under an ice layer, and its depth exceeds 100 kilometers. Theoretical calculation of the formation and evolution processes of such planets was performed by French astrophysicists led by Christophe Sautin in 2004. According to this theory, if a forming planet's mass exceeds 10 Earth masses, it begins actively attracting hydrogen and helium from the surrounding gas dust cloud, eventually transforming into a gas giant. If the celestial body's mass is only 6 to 8 Earth masses, the new planet will consist of ice and rocky materials in approximately equal proportions. For comparison, the total weight of all water in Earth's world ocean is only 0.025% of our planet's total mass. If the cosmic object's orbit is located far from its parent star, it will become an ice giant or cold super-Earth. Radioactive decay inside the core can melt part of the ice, leading to the formation of a hidden ocean. But the celestial body's outer layers will remain frozen. If the planet ends up in its star's habitable zone, its outer layers will melt and cover the surface with a boundless ocean. Theoretical calculations show a planet with a mass of 6 to 8 Earth masses can have a water shell exceeding 100 kilometers. The pressure of such a water column can reach 20,000 atmospheres, depending on temperature, impurities, and other parameters. This is enough for the formation of special exotic forms of ice that can remain solid even at high temperatures. Moreover, unlike familiar ice, these modifications are heavier than liquid water. For example, Ice 7's density, most probable in these conditions, is approximately 103 pounds per cubic foot. This ice settles on the planetary ocean's bottom, forming a massive cryosphere that surrounds the planet's heavier core. The opportunity to check these theoretical calculations in practice appeared when a small, dim star receiving the designation Gliese 1214 was discovered 42 light-years from Earth. The red dwarf's diameter turned out to be 5 times smaller than the Sun's, and its mass is only 15.7% of the Sun's. Moreover, Gliese 1214 is 300 times dimmer than our star, and its surface temperature equals only 4,940 degrees Fahrenheit. In itself, the star doesn't represent anything special, just another unremarkable red dwarf, similar to billions of other stars in our galaxy. However, in 2009, a single planet was discovered near it, receiving the name Gliese 1214b. While its diameter is 2.5 times Earth's, this exoplanet is only 6.5 times heavier than Earth. Simple calculations show that with such parameters, gravitational acceleration on the planet's surface will be only 91% of Earth's indicator. Gliese 1214b's average density equals approximately 117 pounds per cubic foot. This value is too low for rocky materials and metals to constitute the exoplanet's main mass, as for example with Earth. However, such an average density value agrees well with the assumption that the planet is 3/4 water and water ice, and only 1/4 rocky materials. Based on these observations, we can assume this celestial body represents an ocean planet. The object is located very close to its parent star. The average distance is only about 1.2 million miles, or 0.014 astronomical units, which is 75 times less than the distance between Earth and the Sunday. Moreover, the orbit's eccentricity is quite high and equals 0.27, slightly more than Pluto's. This means at perihelion, Gliese 1214b is approximately twice closer to its star than at aphelion. The planet completes one full orbit around its parent star in approximately 36 hours. Despite the fact that the red dwarf Gliese 1214 is approximately 300 times dimmer than the Sun, incredible proximity to the star makes the planet's climate very hot. If we assume Gliese 1214b's surface has a reflection coefficient like Venus, the planet's surface temperature should be about 248 degrees Fahrenheit. If it's darker, the temperature can reach 536 degrees Fahrenheit. Thanks to the fact that Gliese 1214b's orbit crosses the star's disk, scientists can conduct spectroscopic studies of its atmosphere, but the results obtained to date are contradictory. If this cosmic object truly is an oceanic planet, its atmosphere should consist predominantly of water vapor with admixtures of other gases. However, in the planet's spectrum, neither hydrogen nor helium nor complex substances like water, carbon dioxide, or ammonia have been detected yet. It's assumed the outer layer of the dense atmosphere is hiding its true composition. Most of all, conditions on Gliese 1214b's surface resemble the insides of a giant steam boiler. Moreover, atmospheric pressure in its lower layers should be at least 15 times higher than Earth's. Due to the fact that the ocean is in thermodynamic equilibrium with the atmosphere, the boundary between them is a rather blurred concept. After all, water vapor's density at the ocean's very surface is approximately equal to constantly boiling water's density. If we begin descending into the ocean's lower layers, pressure will continuously grow until at a depth of about 60 miles, it reaches such values that water can no longer remain liquid even at such high temperature. We'll reach ice composed of dense and heavy ice, whose thickness by calculation can exceed 3,000 miles. Thus, most of the water on the planet is concentrated precisely here. Below the cryosphere, most likely is a core of rocky materials and metals. Unfortunately, life's emergence on any ocean planet is unlikely, even if the surface temperature were more favorable. The fact is that the ocean on such exoplanets contains too few trace elements necessary for living creatures. Even considering meteorites rarely bombarding these celestial bodies' surfaces, the diversity of chemical compounds isn't enough for life formation. Nevertheless, studying oceanic planets presents enormous interest for science. NASA mathematical modeling calculations, published in 2020, state that billions of planets of this type may exist in our galaxy, both cold ones with oceans hidden under ice crusts, and warm ones similar to Gliese 1214b. After all, water is one of the most common complex compounds in the universe. This means the chances of finding new ocean planets are quite high. C.W. Leonis, a dying giant. At 650 light-years from Earth lies a magnificent star named IRC +10216, also known as CW Leonis. At its pulsation peak, its radius can reach 560 solar radii, which is approximately 2.6 times the distance from Earth to the Sunday. If we mentally placed CW Leonis at our system's center, its surface would engulf all planets up to Mars and reach the asteroid belt's inner boundary. Meanwhile, the star's mass is comparatively modest, ranging from 1.5 to 4 solar masses. Its surface temperature is only 3,680 degrees Fahrenheit. However, the star emits on average 8,500 times more energy than our Sun, thanks to its incredible size. Like all red giants, CW Leonis is at the final stage of its life cycle. Its age isn't precisely determined, but it's known to be several billion years old. It's assumed that at the beginning of its journey, the star was a blue-white star with a mass of 3 to 5 solar masses. However, about 1 billion years ago, a significant proportion of hydrogen in CW Leonis's composition burned out, transforming into helium. Gradually sinking down to the star's center, helium displaced the remaining hydrogen, forming a superheated core that doesn't participate in thermonuclear reactions. This process is characteristic of all stars whose mass is close to the Sun's and is the starting point for their transformation into red giants. The star's internal pressure forces it to increase greatly in size, as a result of which the star's outer shells become more rarefied and unstable. The cosmic object's diameter increases dozens of times, and its color gradually changes to blood red. Nevertheless, thermonuclear reaction continues in the star's depths, thanks to which the stellar plasma's pressure and temperature grow. At a certain moment, a chain reaction of helium nuclei fusion with carbon formation begins, the so-called helium flash. This is a complex, multi-level physical process that radically changes the star's internal structure. Its core becomes incredibly hot, while the outer shells, on the contrary, cool and darken. Currently, CW Leonis contains a huge amount of carbon, but its mass isn't enough to transition to the next level of nuclear synthesis. As a result, the thermonuclear fire in the object's interior becomes unstable. When it begins to fade due to lack of fuel and temperature, the stellar material gradually cools and compresses under gravity's action. Because of this, the star's interior heats up again, and the reaction flares with new force. Having received a new portion of thermal energy, the stellar material expands again, interrupting combustion. It's assumed this cyclical process underlies the star's periodic brightness changes. CW Leonis pulsates with a period of 649 days, reaching maximum luminosity 11,300 times greater than the Sun's. At the cycle's lower point, the object radiates 6,250 times more energy than our Sunday. During compression, the upper layers of stellar material partially separate from the star, replenishing the carbon-oxygen gas nebula surrounding the giant. According to calculations, this process forces CW Leonis to lose annually about 4 times 10 to the 22nd power tons of material, which is approximately 7 times Earth's mass. Observations show the circumstellar nebula's age is at least 69,000 years. Moreover, its mass equals approximately 1.5 solar masses, and its size reaches 84,000 astronomical units. The nebula has a complex structure containing thickenings and gas accumulations, as well as semi-arcs and uneven rings. It's believed the cause of this is magnetic activity and stellar wind created by the unstable nearby star. The cloud's chemical composition surrounding CW Leonis arouses enormous interest among researchers. Spectral analysis data show it contains about 70 different chemical compounds, such as carbon dioxide, water, and ammonia. In addition, the nebula contains many elements from the periodic table's upper part up to iron. It's quite probable that in the past, CW Leonis had planets. However, they apparently were absorbed by it even at the expansion stage. In any case, many years of observations haven't discovered obvious traces of their existence. However, back in 1994, barely noticeable distortions of the star's orbit were recorded, and in 2017, mysterious material displacements were discovered in the gas-dust cloud surrounding the star. Their cause may be a small red dwarf orbiting the giant. However, its radiation hasn't yet been detected. The reason for this may be the nearby nebula, which scatters and re-radiates energy flow from nearby light sources. This phenomenon masks any nearby objects, not allowing them to be examined properly. It's assumed the hypothetical stellar companion of CW Leonis's mass is certainly less than the Sun's, and it spends approximately 100 years on a complete orbit around the giant. Another interesting fact is the relatively high water content in the star's vicinity and shell. Initially, it was believed the star, expanding, melted and absorbed ice comets. However, observations conducted in 2009 showed that some spectral lines' temperature reaches 1,340 degrees Fahrenheit, which is only possible if water vapor forms directly in the giant's outer shells. This fact didn't fit the recognized model of red giant structure at that time. According to it, all oxygen contained in stellar material necessary for water synthesis should have completely gone to carbon monoxide formation. A new hypothesis was proposed to explain what was happening. According to it, silicon and carbon oxide molecules are destroyed by powerful ultraviolet radiation. After this, the freed oxygen reacts with hydrogen, forming superheated water vapor. This assumption's weak point remains the question about the ultraviolet source. Such reactions can only proceed at sufficiently high temperature, that is, inside stellar material. However, it practically doesn't transmit cosmic rays. This paradox can be resolved by assuming that due to the star's instability, large ruptures and areas with reduced density periodically arise on its surface, more open to ultraviolet. The total mass of water vapor in the atmosphere and stars' outer shells is estimated at several quintillion tons. This magnitude seems huge, but in reality, water constitutes only about 1/1000th of the star's total mass. According to modern concepts of stellar evolution, CW Leonis is living out the last moments of its life as a red giant. Within the next 10 to 30,000 years, it will finally exhaust its stellar fuel, after which it will shed its outer shells in a powerful explosion. In the star's place will remain an incredibly hot and dense cosmic object, a white dwarf. Its mass will be about 80% of the Sun's, and its temperature in the first seconds after formation will reach several million degrees. However, without an energy source, it's doomed to billions of years of slow but inexorable fading. Ultimately, the celestial body will become almost invisible against the cosmic void's background, transforming into a mysterious black dwarf. But this will happen very, very soon. The shock wave and off-the-scale temperature at the explosion's center will give birth to new elements impossible to obtain in stars' interiors. For example, uranium, gold, and lead. Subsequently, they'll become part of new celestial bodies. Millions of years later, radioactive decay will warm planets' interiors, melt ice, and saturate oceans with trace elements, creating conditions for life's emergence. The universe is constantly evolving, and this process is unthinkable without global cataclysms and destruction. But ultimately, after every storm follows a new dawn. The most extreme exoplanets. Earlier, we've already managed to study some terrifying and deadly dangerous worlds discovered in the universe's expanses. Some of them are extremely hot. Others are located near powerful radiation sources, and still others are noted for unusual conditions reigning on their surfaces. However, our list of the most terrible planets isn't yet exhausted, which means it's time to continue this journey. Our first stop is 202 light-years from Earth, near the orange dwarf K2-141. Its mass equals approximately 0.7 solar masses, and its radius is 68% of our star's corresponding parameter. Moreover, the star's surface temperature reaches 8,000 degrees Fahrenheit, which is approximately 20% less than the Sun's. At a distance of only 0.007 astronomical units from the star, you can discover a rather unusual planet called K2-141b. This rocky world is 5 times more massive than Earth, and its radius is 1.5 times our planet's corresponding indicator. From this data, we can conclude that surface gravity is at least twice Earth's, and the heavy metallic core constitutes 30 to 50% of its mass. The celestial body completes one full orbit around its parent star in approximately 6.5 hours. Moreover, due to extreme proximity to the star, it's tidally locked and constantly faces it with one side. Observations show temperature on the object's illuminated part reaches 5,400 degrees Fahrenheit. This is enough not only to melt most rocks and metals, but also to convert them to vapor. It's assumed the planet's day side may be covered with an eternally boiling lava ocean and also have an exotic atmosphere consisting of heavy metal and silicate vapors. Meanwhile, the celestial body's shadow region is incredibly cold. According to calculations, most of its temperature is dozens of times lower than on the illuminated side, and can approach negative values. Mathematical modeling shows that due to such temperature difference, the planet constantly has the strongest winds, whose speed reaches 1.1 miles per second. This is approximately 5 times the speed of sound, meaning K2141b's surface is constantly shaken by the most powerful deafening roar. Its assumed atmospheric flows, having reached the planet's shadow side, condense and fall as blazing rain on its surface, forming lava rivers. Thus, molten metal returns to the magma ocean, then evaporates again, forming an incredible fiery cycle. However, this entire hellish cycle affects only a comparatively small area of the planet's shadow part. This is because evaporation from the heated side simply doesn't reach the unlit area's main part, settling in the border zone. Therefore, the dark side's central region most likely represents a frozen desert, bound by layers of solidified rock. Nevertheless, K2141b is far from the hottest planet among known ones. For example, 670 light-years from Earth is located an object named Kelt 9b, whose surface is heated to 7,800 degrees Fahrenheit. Moreover, almost all red dwarfs' outer shells are noticeably cooler, meaning this exoplanet can compete in temperature with stars. Its parent star, known as Kelt 9, is a blue-white star whose mass exceeds the Sun's by 2.6 times. Moreover, the object's diameter is 2.3 times the Sun's corresponding parameter. Kelt 9's surface temperature is quite high and equals approximately 17,540 degrees Fahrenheit. It's precisely this fact that largely explains such extreme conditions reigning on the nearby planet. Kelt 9b is located 0.035 astronomical units from its parent star and completes one full orbit around the system's center in approximately 1.5 days. The exoplanet is a hot gas giant whose mass exceeds Jupiter's by 2.8 times, and its radius is approximately double. Based on modern concepts of this planet-type structure, we can assume this celestial body's atmosphere's internal part is even hotter. According to calculations, its temperature can reach 19,340 degrees Fahrenheit thanks to heavy metal ionization processes. This value is so great that besides familiar substances like hydrogen or helium, in the planet's gas shell, you can also encounter iron and titanium vapors. Proximity to the parent star and extremely high temperature lead to the planet gradually losing its atmosphere. The most powerful stellar wind constantly blows it into cosmic space, so the object is surrounded by a rarefied gas cloud. Subsequently, this material will be attracted and absorbed by the star. Calculations show the exoplanet loses up to 68 Earth masses every billion years. Theoretically, after a prolonged time, Kelt 9b could lose all its atmosphere and transform into a chthonic planet. However, its parent star will most likely reach its life cycle's final stage long before this moment, while absorbing and destroying all nearby celestial bodies. V. 391 Pegasi b, the survivor. The previous cosmic objects are evidence that stars can not only warm nearby planets, but also destroy them. However, in the universe exist celestial bodies that experienced their parent star's wrath like no other. One of them is located 4,570 light-years from Earth, near a small star named V391 Pegasi. This star is a white dwarf, with twice less mass than the Sun's and a radius about 23% of our star's corresponding parameter. This astronomical object's temperature is very high and is almost 54,000 degrees Fahrenheit. However, thermonuclear reactions in its interior ceased long ago. Now the star awaits hundreds of billions of years of slow cooling and transformation into a black dwarf. Near this unremarkable star orbits a planet with an amazing fate, which bears the name V391 Pegasi b. Mathematical modeling shows it not only survived the progenitor star's shell shedding, but also for some time moved practically inside it. It's assumed that when the star at the system's center transformed into a red giant, its outer shells approached very close to the planet's orbit and became extremely rarefied. Their density turned out to be dozens of times less than our familiar atmospheric air, meaning celestial bodies absorbed by the dying star maintained integrity for some time. Of course, they gradually lost speed and descended into the star's hotter, denser layers. However, the star shed its outer shells before V391 Pegasi b melted and ceased to exist as a whole. Currently, this exoplanet is most probably a gas giant 3 times more massive than Jupiter. Its orbit is located approximately 1.7 astronomical units from its parent star, and the object requires about 1,170 Earth days for a complete orbit around the system's center. It's not completely clear how this celestial body managed to preserve such high mass after contact with the star's superheated shells. It's assumed their impact should have completely destroyed the object's atmosphere. However, there's no doubt that the parent star's collapse substantially changed both the exoplanet's orbit and parameters. Therefore, we'll probably never know what V391 Pegasi b represented before it plunged into a sea of raging plasma. PSR J 17-1438. The Diamond Planet. Cosmic expanses hide many astronomical objects with the most unusual properties. Some of them are practically impossible to notice in an ordinary telescope. However, they can be discovered when studying space in the radio range. Examples of such celestial bodies are pulsars, neutron stars rotating around their own axis at enormous frequency. Such object spectra are characterized by very fast and even pulsations. Therefore, when a foreign celestial body passes between the radiation source and Earth observer, it's immediately noticeable. This is exactly how our next target was discovered. It's located approximately 4,000 light-years from Earth and is situated near a neutron star with a hard-to-pronounce name. The pulsar's diameter is only 12 miles, and its mass equals approximately 1.4 solar masses. The object rotates at incredible speed, making about 10,000 revolutions per minute, constantly emitting powerful electromagnetic radiation pulses. These waves of deadly radiation constantly irradiate the exoplanet's surface, making it a harsh and unfriendly place. The celestial body itself completes one full orbit around the system's center in only 2 hours, and its distance from the pulsar is less than the Sun's radius, only 370,000 miles, or 0.004 astronomical units. Meanwhile, the planet's surface is bound by eternal cosmic cold, as its parent star practically doesn't radiate thermal energy. The object's mass is about 330 Earth masses, and its radius is approximately 4 times larger than our planet's. Thus, surface gravity is approximately 20 times Earth's. Calculations show the planet's average density is approximately 144 pounds per cubic foot. This is more than most known compounds. It's assumed the object consists predominantly of crystalline carbon under enormous pressure. In addition, its upper layers contain some oxygen, which most likely is in chemical bond with carbon. It's very unlikely the celestial body located so close to the star could have survived the supernova explosion. Most likely, this exoplanet formed after the progenitor star finished its journey, leaving behind a pulsar. Another hypothesis states this object may be remains of a white dwarf that lost most of its material. In this case, classifying such a celestial body becomes a very complex task. Be that as it may, this world is indisputably one of the most dangerous and unfriendly among those hiding in the cosmic abyss. Black holes, the ultimate darkness. Obviously, discovering a celestial body that absorbs all light falling on it is a very difficult task. Therefore, currently not so many confirmed black hole candidates are known. Nevertheless, mathematical modeling shows that in our galaxy, their number may reach 100 million. This number seems huge, but if you consider the Milky Way holds from 200 to 400 billion stars, it becomes obvious black holes are quite rare objects. In one of our past episodes, we already determined that to become a black hole, the progenitor star must have a mass of at least 18 to 20 solar masses. Only in this case will the supernova explosion be strong enough to compress the star's superheated core into a super-dense matter clump. After this, nothing can overcome the object's attraction and leave the boundaries of the so-called Schwarzschild sphere. In the dead star's place will remain a mysterious object whose internal structure can no longer be described by known physics laws. One of the closest black holes to Earth is an object named A62000, or V616 Monocerotis. It's located approximately 3,300 light-years from Earth and is part of a binary star in the Monoceros constellation. The system's second component is an orange dwarf with a mass about 50% of the Sun's. Every 7.75 hours, it completes one full orbit around an invisible object of unknown nature. Calculations show this hidden celestial body's mass is about 6.6 solar masses, which is too much for a neutron star. This means the mysterious object is most likely a black hole. The more massive neighbor's attraction not only deforms the star, giving it an elongated shape, but also strips its outer layers of stellar material. Spun-up streams of superheated gas gradually flow toward the black hole, forming a bright accretion disk, thanks to whose radiance it was discovered. In V616's vicinity are located at least several dozen stars, some of which most likely have their own planetary systems. It's quite probable that in the future, One of these stars may approach the black hole, resulting in capture by the object's monstrous gravity. In this case, it awaits the same fate as the current companion. The process of a black hole's interaction with other objects largely depends on their mass ratio. The smaller the distance between celestial bodies and the more massive the black hole, the stronger tidal forces affect its companion. They can deform the star, stretching it toward the system's common center of mass, and even form channels through which stellar material will flow closer to the black hole, replenishing its accretion disk. If tidal forces prove sufficiently large, they can completely destroy the absorbed object, transforming it into a fiery ring. It's assumed that, hypothetically, planets can orbit a black hole, just as around an ordinary star. Contrary to popular opinion, black holes don't possess the ability to uncontrollably and inexorably pull all surrounding objects inside themselves. From gravity's standpoint, on cosmic scales they behave analogously to a star of the same mass. Therefore, a black hole could quite possibly have a stable planetary system. There are several possible paths for their formation. First, the source of new celestial bodies can be the gas-dust nebula formed as a result of the supernova flash. Under gravity's action, material clumps first form in it, which collide with each other and attract cosmic dust. Ultimately, planets and satellites are born, as well as numerous small celestial bodies, such as asteroids and comets. Moreover, the black hole's hot accretion disk radiation may be sufficient to warm them and even melt surface ice. Hypothetically, such a planetary system could be favorable for life's emergence. Second, when a black hole captures and destroys another planetary system, some objects in its composition may occupy stable orbits around the new mistress. Of course, as a result of this process, conditions on celestial bodies' surfaces may radically change. Thus, an ice giant may transform into an ocean planet, and a gas giant may lose almost all hydrogen and turn into a chthonic planet. Third, wandering celestial bodies, such as rogue planets or interstellar asteroids, will also be attracted to massive objects. And although such systems haven't been reliably discovered yet, there are no prerequisites to consider them impossible. If a planet is located very close to the system's center and the black hole has sufficient mass, other factors come into play. The superheated material stream forming the accretion disk will strip the celestial body's atmosphere, and friction will slow it, increasingly pulling it toward the black hole. Eventually, the strongest tidal forces will tear the planet into the tiniest pieces. The formed fragments will continue moving in the accretion disk, gradually dissolving in the surrounding hot gas. Ultimately, they'll inevitably be absorbed by the black hole, becoming its integral part. Types of black holes. It's believed 3 main types of black holes exist in the universe, differing primarily in mass. The first type can be found at most spiral galaxies' centers. These are giant black holes whose mass can reach several billion solar masses. Matter density in the galaxy's central part is usually very high, leading to the formation of many closely located large and bright stars. Rapidly burning out, they transform into black holes that rapidly grow and often merge with each other. Ultimately, supermassive objects are born, surrounded by gigantic accretion disks consisting of superheated matter. Their radiance can be seen from billions of light years away, even if the galaxy itself isn't visible at all. We call such objects quasars. The second type is much more widespread but also much harder to notice. It includes black holes whose masses are close to stellar. They form from large stars at the end of their life cycle. Absorbing other celestial bodies and interstellar gas, these objects gradually grow, transforming into intermediate mass black holes. They can also merge with each other, creating gravitational waves that distort space for many light years around. The third type is hypothetical primordial black holes. Their existence follows from modern theory of the universe's origin and evolution. Fluctuations and oscillations in matter filling cosmic space at early stages of its development could lead to black holes' formation of arbitrarily small sizes. It's worth considering that, according to calculations, the smaller an object of this type, the faster it evaporates at the end of its life cycle, transforming into the most powerful electromagnetic pulse. Modeling shows primordial holes with a mass of about 10 to the 12th power kilograms should flash approximately in our time. However, until now, not a single such event has been recorded. Additionally, there's a hypothesis that as a result of ultra-high energy elementary particle collisions, a microscopic black hole can form, also called quantum. At the same time, conditions necessary for such an event are currently impossible to create under laboratory conditions, and these hypothetical objects' calculated lifetime is so small that measuring it using modern methods is extremely difficult. Therefore, quantum black holes still remain only a hypothesis. Of course, detecting such dark and compact objects is quite difficult. Some of them have a stellar companion whose anomalous movement allows detecting the invisible companion. Another common method's basis lies in observing accretion disks. Such objects' spectra have characteristic features allowing them to be distinguished from other cosmic light sources. In some cases, it's possible to obtain a disk image with a black spot inside, which proves the observed object's unusual structure. Also, a black hole can be discovered thanks to gravitational microlensing effect. For this, a massive, invisible object must pass between Earth and a distant star, characteristically changing its spectrum. Obviously, applying this method requires many rare factors to coincide. With all this, there's no doubt space is filled with many dark and barely noticeable celestial bodies. Among them may be wandering black holes, mysterious objects wandering in interstellar space and absorbing without remainder the tiniest light particles will most likely remain unexplored for us. The Milky Way, our galactic home. Long before the telescope's invention, people observed a bright band crossing the sky. The beautiful, mysterious phenomenon gave rise to many legends, but thousands of years of science development were required to explain it properly. The Milky Way turned out to be not God's path, but scattered light from billions of stars, too distant to see each one individually. The thought that surrounding stars could be part of a single structure of incredible size was first expressed by Immanuel Kant back in 1755. He also suggested some nebulae discovered by astronomers might represent distant star clusters, that is, other galaxies. This brilliant guess was ahead of its time and was initially rejected by the philosopher's contemporaries. Only in the early 20th century did observational technology development allow confirming other galaxies' existence. And in 1936, Edwin Hubble created their classification, many provisions of which scientists still use today. According to this system, the Milky Way belongs to barred spiral galaxies, though it acquired its current appearance far from immediately. Our galaxy is comparatively old, as stars in its central globular clusters are about 13 billion years old, and most thin disk objects appeared about 8.8 billion years ago. At the same time, active star formation continues in separate sections of the Milky Way, meaning young stars constantly appear. Collected data indicates the Milky Way is a comparatively large galaxy. Its disk's diameter reaches 200,000 light-years, and the halo extends considerably farther into space's depths. Our galaxy contains at least 200 billion diverse stars, as well as 25 to 100 billion brown dwarfs. In addition, it includes more than 1 trillion planets and countless small celestial bodies, as well as cosmic dust clouds and interstellar gas that can reach gigantic sizes. Moreover, ordinary matter constitutes only a small fraction of the galaxy. About 90% of the Milky Way's total mass falls to so-called dark matter. This mysterious but widespread in nature substance practically doesn't emit light, but actively participates in gravitational interaction. Despite the fact that most galactic mass remains invisible, we can still calculate it. For this, researchers use star trajectory around the Milky Way's center. According to performed calculations, our galaxy's total mass lies within 0.8 to 1.5 trillion solar masses. The Milky Way has a complex structure, and our journey will begin from its center. This galaxy region is surrounded by massive gas and dust clouds, but thanks to happy chance, we can observe it through the so-called Barday's window, a cosmic space section with reduced dust content. Like most spiral galaxies, the Milky Way's center is occupied by a supermassive black hole surrounded by an accretion disk with a radius of about 3 light-years. It received the name Sagittarius A star and is the closest cosmic object of this class to us. Its mass is 4.3 million solar masses, and its radius doesn't exceed 10 million miles, which is 3 times less than Mercury's orbit. At first, data about the object's nature at our galaxy's center were obtained as a result of long observations and careful calculations. And only quite recently, on the 12th of May 2022, using the EHT radio telescope network, a photograph was obtained confirming previous hypotheses. The galaxy center's vicinity is a very densely populated area. Within 3 light-years of the black hole, more than 6,000 stars have already been discovered, and some of their orbits are quite precisely determined. For example, the blue-white star named S62 in its orbital motion approaches the black hole at a minimum distance of 17.8 astronomical units, reaching a speed of 6.7% of light speed. Such a fast star's movement trajectory can no longer be described by classical mechanics laws due to relativistic effects. For example, its orbit's axis shifts approximately 75 arc-minutes with each revolution. Additionally, crossing this part of space, we can notice several large star clusters with a total mass of about 1 million solar masses. And a bit farther, at a distance of about 200 light-years, with high probability, another giant black hole is hiding, approximately 100,000 times more massive than the Sunday. Further movement will allow us to reach the central molecular cloud, an irregularly shaped region, 1,600 to 1,900 light-years in size, whose total mass exceeds 60 million solar masses. Here are located many stellar nurseries and gas nebulae, as well as protostars and supernova remnants. Most of the cloud's material is dense hydrogen, whose temperature fluctuates from 50 to 600 Kelvin, corresponding to a range from -370 to +620 degrees Fahrenheit. Spectral analysis shows that, besides hydrogen, the giant nebula also contains carbon monoxide, methyl alcohol, and hydrogen cyanide. Flying a bit away from the Milky Way's center, we'll be able to notice it's surrounded by a bulge, a bright and massive elliptical-shaped thickening. Its length reaches 10,000 light-years, and its transverse diameter is about 7,000 light-years. The bulge's total mass is about 10 billion solar masses, and it's extremely difficult to count the exact number of stars because their radiation merges with each other. Thanks to its elongated shape, the bulge forms the so-called bar, about 13,000 light-years long, which serves as the foundation for spiral galactic arms. It's precisely here, at one of its ends, you can discover the Stephenson 2 star cluster, containing the largest star known at present. It bears the name Stephenson 2 to 18, and its radius is 2,150 times the Sun's. Unfortunately, the probability of discovering exoplanets near such an outstanding object is extremely low. If they ever existed, the hypergiant surely absorbed them during expansion. The galactic center includes billions of stars and, apparently, an enormous multitude of exoplanets. However, the probability of meeting a potentially habitable world among this abundance is much lower than in less populated galaxy regions. The reason is that many close stars destabilize exoplanets' orbits, and their powerful radiation carries deadly radiation. Therefore, a special region called the habitable zone is distinguished in the galaxy. It represents a ring with a radius from 22,000 to 29,000 light-years and includes star systems with the most favorable conditions for biological life's emergence. Worlds inside this ring suffer from radiation, and beyond its boundaries, from heavy element deficiency. However, mathematical modeling shows stars inside galaxies can migrate distances of thousands of light-years, thus leaving the habitable zone or replenishing it. Consequently, an exoplanet's presence within this region doesn't yet guarantee favorable conditions on it. The galactic disk. If we continue moving away from the Milky Way center, we'll be able to see its most impressive part, the galactic disk. It consists of two components with different properties. The first of them, the the so-called thin disk, has a thickness from 1,000 to 1,300 light-years and a visible radius of about 50,000 light-years. Further, it gradually disperses, and its most extreme stars are removed from the galactic center to a distance of up to 100,000 light-years. This part of the Milky Way contains about 80% of the galaxy's visible mass and formed later than its other components. The thick disk is comparable to the thin one in diameter, but 4 times thicker and much more rarefied. It consists of old stars and almost doesn't contain interstellar gas. Observations of some Milky Way stars, combined with mathematical modeling, testify that in the period from 11 to 8 billion years ago, our galaxy absorbed another. This hypothetical cosmic structure received the name Gaia Enceladus. It's believed it gave the Milky Way several billion stars, as well as enormous amounts of interstellar gas and dark matter. Thanks to this grandiose event, most of our galaxy's thick disk formed, and the additional gas influx provoked a star formation burst. Undoubtedly, the disk's most noticeable structural elements are the spiral arms. Usually 2 main ones are distinguished, which bear the names Centaurus and Perseus, and 2 secondary ones, Norma and Sagittarius. Sometimes a 5th large arm is also distinguished, named after the Cygnus constellation. Galactic arms are regions of increased star concentration. Also, most interstellar gas is concentrated here, thanks to which 3 to 5 times more young stars form in the arms than the galactic average. The first millions of years of their lives, they spend in open clusters. However, gravitational forces aren't enough to hold stars together for a long time. For this reason, clusters become unstable, and young stars gradually move away from each other. Moving along the Sagittarius arm, we'll reach a branch connecting it with the Perseus arm. This stellar structure's length reaches 11,000 light-years, and its width is approximately 3,500 light-years. It's called the Orion Arm, and it's precisely here, at a distance of 27,000 light-years from the galaxy's center, the solar system is located. If we turn our gaze from our planet toward the galaxy's center, we can see a dark abyss. There's located the Great Rift, blocking a substantial part of the Milky Way from us. This cosmic space region is filled with massive interstellar dust and gas clouds, with a total mass of about 1 million solar masses. Despite the fact that in the optical range the rift is practically opaque, its material actively emits radio waves and thermal energy. According to spectral analysis data, the clouds consist mainly of hydrogen, with a small fraction of more complex compounds, ammonia, alcohols, and even amino acids. It's assumed the Great Rift is a potential star formation hotbed. However, the nearest stars will flare in it very soon indeed. Until this happens, we'll head further, beyond the galactic disk's boundaries. The galactic halo, despite the fact that its bright and noticeable arms attract much attention, the Milky Way isn't limited only to this region. A careful look will allow us to notice the most extensive and simultaneously most rarefied component, the halo. Its visible part has a spherical shape and extends to a distance of up to 260,000 light-years from the galaxy's center, but contains only a few % of its total mass. The halo includes many globular clusters consisting of very old stars over 12 billion years old, as well as several grandiose stellar streams. For example, the Sagittarius stream, formed by several thousand stars, encompasses our galaxy with an elongated ellipse located almost perpendicular to the main plane. Modeling shows that with high probability, all these stars were captured by the Milky Way's gravitational forces from the dwarf satellite galaxy named Sagittarius Dwarf Elliptical Galaxy. It's located 50,000 light-years from the Milky Way's center, and within several billion years will be completely absorbed by it. A similar fate has almost befallen another dwarf galaxy, located in the Canis Major constellation. The Milky Way has practically destroyed it, pulling millions of stars into its gravity. A chain of stars with a total mass of about 100 million solar masses has already wrapped around our galaxy 3 times, stretching for 200,000 light-years and mixing with other stars. Besides bright but rare stars and clusters, the halo includes enormous amounts of gas, whose temperature reaches millions of Kelvin. In addition, it's assumed that in the Milky Way's vicinity is scattered a large amount of dark matter, forming the so-called dark halo. Extending to a distance of up to 2 million light-years, it practically doesn't emit electromagnetic radiation and can be detected only by gravitational interaction. Nevertheless, the dark halo makes a substantial contribution to our galaxy's global stability, remaining until now an unsolved mystery. Closing thoughts. The diversity of cosmic objects is truly incredible. Some of them are encountered everywhere, while others can be considered unique. Every corner of space holds many mysteries, resolving which will receive new knowledge about the surrounding universe. Will we one day solve all its secrets? Only time will tell. As we drift through this cosmic journey, remember that we are part of this grand tapestry. Our solar system, a tiny speck in the vast Milky Way, orbits peacefully in the Orion Arm. We're traveling through space at nearly 500,000 miles per hour. Yet from our perspective, everything seems still and calm. The stars you see in the night sky are our neighbors in this cosmic neighborhood. Some are being born in stellar nurseries, while others are in their final death throes, preparing to seed the galaxy with the elements necessary for new worlds, new stars, and perhaps new life. The Milky Way continues its eternal dance through the cosmos, slowly rotating, slowly evolving. In about 4 billion years, it will collide with the Andromeda Galaxy, our nearest large galactic neighbor. But that collision will be a gentle merger, a cosmic ballet lasting millions of years. For now, we can simply marvel at the beauty of our galactic home, from the supermassive black hole at its heart to the mysterious dark matter in its halo, from the youngest stars blazing brilliantly in spiral arms to the ancient stars that have witnessed nearly the entire history of the universe. As you close your eyes tonight, imagine yourself floating among these stellar wonders, drifting past glowing nebulae where new stars are being born, sailing through the spaces between spiral arms where darkness reigns but is punctuated by distant points of light. You are made of star stuff. The atoms in your body were forged in the hearts of dying stars billions of years ago, You are, quite literally, the universe experiencing itself. Rest now, cosmic traveler. The stars will continue their eternal dance, the galaxy will keep spinning, and tomorrow you can look up at the night sky with new eyes, knowing you've journeyed through the Milky Way. Sleep well under the light of ancient stars. Our journey through the cosmos continues, always continues, in the endless depths of space and time. Good night.